Here, I'm going to talk about FEMM. This is a free tool. It's a good tool. Somebody who wants to design motors and doesn't want to spend money on a finite element analysis tool, this is a good tool to have. It's easy to use and quite effective. We have verified FEMM with respect to motor solve, and the accuracy is pretty good in terms of the performance. Okay, so let me give you. So finite element, so FEMM is basically a nickname for finite element method magnetics. It was developed by David Meeker, a software used for magnetic analysis of motor drives. It's actually used for a number of other functions as well, including heat, thermal problems as well. Solve problems like interactive shell and mesh generation. Results can be extracted using graphical techniques. So it solves magnetic and electrostatic issues, and I'll give you an example here. So you can pick a problem. For example, when you start the program, you can select a problem type. You can have a magnetic, electrostatic, heat flow, or current flow. So these are the four problem areas you can handle. So defining problem to solve. So here, normally you have to select planar, length in millimeters, and you define frequency 0 hertz. Depth is your stack length. Basically, you're looking at the motor. So here you can put the stack length. Solver precision, you can come back and adjust that. Minimum angle, and the AC solver. I'm not sure what the minimum angle is. For this precision, you can either wax it or make it tighter. Okay, an AC solver is basically successive approximation. That's the engine it uses to solve the finite element analysis problems. So you do have to define a boundary to a problem. Without a boundary, it cannot solve. There has to be a boundary you describe. The boundary is defined for obtaining a unique solution, and you basically set the boundary as a new boundary, and I'll show you how you do that in your problem. And that basically restricts all your fields to be within that boundary. So here you can set all these to zeros and all these also. Okay, so then you have workspace toolbar. These here toolbars are for design. 1, 2, 3, 4, 5 are for designing purposes. These are for analysis. So, for example, this one, we select a node. This one, draw a line. This one, draw an arc. This one, you have place and select materials. This one, select the objects. And then this one, you create a mesh, finite element analysis mesh. This one, you create a running simulation, and this one is for doing the results. So here you have a motor which has been imported. We drew this motor in SolidWorks, and then we can import that motor into the FEMM. So there is some you may lose the arcs lost in importing, so you have to reconnect these points after you have finished importing the motor. So here you have a material selection. They have a decent selection of materials. You have air, permanent magnet materials, ceramic magnets, samarium, cobalt magnets, soft magnetic material, low carbon steel material, magnetic stainless steel, silicon iron, cobalt, nickel, and solid non-magnetic conductors, right? So you basically end up selecting some of the materials and putting them on the right side of things that you can use after you have selected your objects. Okay, So select circuit property from toolbar and define coil and phases, define the property. So once you have defined your geometry, you're going to look at the coil, define the coil, and then give it a name. For example, here the property is coil A. Then placing of circuit material and type of gauge we use. So here we say, okay, we're going to use a 26 gauge wire. We're going to put it. Now you can also combine various elements into groups, right? So here we have a group 2. And so this is your coil B. We say number of turns is 148, 26 gauge wire, and it is going to be group 2. Select the material, select the coil, select the number of turns. And then defining the winding material, you can click on this button and it will place a point. For example, here, this is a magnet. This shape here is your stator core. These rectangles are your windings, okay? So block drawn to represent the windings, we have to set the number of turns in the material selection pop-up. And so we do right click for editing it, and you can pick the material. This has to be copper material, gauge of 26 numbers of turns, etc. The one we want to add. All right, so and then you have stationary type group, which would be your, in this case, your stator. This is the outer rotor motor, so your stator is stationary inside. And the rotating parts you can put under a single group, which will be outside, that be your rotating rotor part. And then you can select different materials, different portions to edit them or to change their properties. Okay, so resistive losses, you select all the windings and you can put them under a group. So that is defined as resistive losses. And then once all that is done, you can do the meshing. And once the meshing is done, you can run the solver and then you can see the results. Okay. So here is a result window. You can see what is happening to your, so here is flux distribution analysis, right? So you can look at how the distribution is. You can also rotate your rotor for different positions so that you can see the flux density at different rotor positions and different currents. So here is a flux density plot with colors, with FEMM output window, and then you have resistance calculated from the toolbar by selecting the tool, where it shows you total current is 2 amps. You can probably see, I don't know whether you can see or not, small, even a big screen, voltage drop, and your power loss of 27.4 watts here. You can do vector plots as well. And then you can use MATLAB to run the whole thing. FEMM has built-in functions and macros that can be used in MATLAB for data analysis and data extraction. Simulation can be automated using MATLAB. To use this macros, we have to add the FEMM folder path to the MATLAB execution path. And once the path has been added, you can access the FEMM functions to MATLAB. Okay, so, and I'll show you an example, hopefully, before we finish the workshop, so you can get an idea. So the MATLAB process, the basic idea is to get the torque and flux values at different currents and different angles. So we want to rotate the motor, and we want to get the different flux densities and torque values at different currents and angles. If you do it without MATLAB, every time we have to change currents manually, run the simulation, and import the data. But if we automate the process through MATLAB, then everything can be done just by running a MATLAB code. And I'll show you a MATLAB code as well, so you kind of get an idea. And I'll put some of these files where you can access it, and you can also see what's happening. All right, so so let's move forward. Okay, so FEMM file location, you want to put your FEMM file location the same as your MATLAB folder under your documents, and then your MATLAB command file in the above location, and then you open your MATLAB file, and then you add your FEMM MATLAB code, execution path, and then input phase current and speed values. So we'll go through an example of this, okay? So this is your flowchart for MATLAB data execution. You prepare your FEMM model, input the peak phase current values simulated. And then here you have user inputs of speed coming from MATLAB here. And you can calculate the mechanical torque, the flux linkage, the current, electrical output power, and mechanical power. So all these can be calculated. So here you use the command path tool to add the FEMM directories into the MATLAB, right? So when you install FEMM 4.2, you will see these 5 directories you need to add using the path. Okay, and MATLAB script open FEMM command is used to call FEMM from MATLAB. Individual function commands are used to call each function for accessing FEMM specific tasks. All the instructions are executed sequentially. Results are extracted in same pattern and stored in .txt files. So MATLAB script examples, open document, specify the FEMM file name here. We'll see an example of that. MI underscore modify circuit properties. Here you can put what the phase current value is. MI analyze, it'll analyze the circuit. MI load solution, show density plot. MO group select block, and torque is MO block integral. All right, that's how you calculate the torque. So create the directory in MATLAB folder path. Extracted results from MATLAB are stored in .txt files. Flux information for different phase current. Torque at different magnetic angle. Torque versus phase current relationship and magnetic saturation. Okay. So here is the example we will see when you see the outer rotor motor. These are stator teeth. The rotor magnets are here outside. Rotor back iron is outside, and your stator slot for windings are inside. And this is 22 millimeter stack, right? So mechanical dimensions, the one example I have, I'm going to show you inner diameter is 366 millimeter, outer diameter is 410 millimeter, air gap is 2 millimeter. Rotor location is exterior, rotor type is surface mount magnets with radial magnets. Number of holes is 28. Number of hole slots is 24. Magnet thickness is 9 millimeter. Back iron depth is 31.2 millimeter. Inner diameter is 180 and outer diameter is 262. So these are what you're able to get. You're able to get for every phase current the torque value. So here we are up to 161 newton meter torque. We are really looking at 5 amps. We want 90 amps, 90 newton meter torque. That's the target. But you can see the flux density is very nominal, 1.65 Tesla here. And resistive losses are very small, 114 watts here, right? It's a pretty big motor, 400 plus millimeter diameter here. So this shows you your graphical flux density for 5 amps of phase current, 1.65 Tesla, no magnetic saturation is observed. I don't have a scale shown here, but this is what it is, 1.65 Tesla maximum. So here is your comparison of torque and phase current. I guess we have already done that, but we did that now for 1, 2, 3, 4 different platforms, 12 millimeter, 22. The 22 was 90 millimeters, and 12 millimeter gives you 50 millimeters, 39 millimeter gives you 150 newton meters, and 66 millimeter gives you 191. right? And then you have losses here, where you can see the losses, how they are progressing with respect to at 5 amps. So a target controller current we want to do, okay? And then you can plot the torque and power with respect to your angle here. And you can see what's happening with your design. Okay, so this is about average current of 92 newton meter, which is what we're targeting. This is 8 amps, 140, and that's the end of the slide. Okay, so this is the end of the slides. So let me show you FEMM software real quick so you can have an idea of what it can do. Let's do this. Okay. So let me open my screen here. So I'm going to share my entire screen so you can see. So this is the FEMM software here, and I can open this design here. Okay, and you can see here essentially you can zoom in, page up to zoom in, and you can see how you bring in a geometry. And here what we have done is you can see we have to align, so I select this here, and I can select this point here, and I can hit space, and I can see it's a neodymium magnet. I have to give a magnetization direction. Here it is theta. I'll show you in a minute what a theta is, okay? So this is, and then this is your coil, and this is coil B. So you have a coil R, coil Y, coil B. So I'm going to select this coil here and tell you, okay, I have got 195 turns, and I have to see how the turns are bound, the direction to the turns, to 20 gauge and coil B is in part of group 2, okay? And then we go and see this coil here, and this one is 200 turns. And that's interesting. Why this matches with this. 200 turns with this one. This has to match with this one, and then 5. They should all be equal. I don't know why they're different, but anyhow, that may be that we are simulating a manufacturing problem here when you have different turns bound by the machine or the worker. So and then let's page down for zoom out, and we're going to look at the air. So inside, this is your air. So I'm going to select this material and hit space, and that's air. There's no properties here. And then we have the back items. I'm going to page out, page down, and page. Let's see if we can find the back item. I'm going to figure the back item is. The back item should be 1020 steel. So this is your boundary condition, and this is your air, right? So basically, you have air between your motor. This is your back iron here. So this is your 1020 steel, and you select that, and you tell you 1020 steel here, and that is part of group 1, which is your rotor group, okay? And then you have, this is the boundary condition here, and then you have air here between this and this. So that's, and then this is your lamination, which is M19 steel. So you click on that, press space that tells you specify. That's interesting. Okay. That should be on 19. Yes. All right, so this is how you specify the whole material, and then you can go and do meshing. So I go here and start meshing it. And mesh, it says created with 25,114 nodes. And I want to go and inspect the mesh, make sure there are no gray triangles, because gray triangles mean there are some undefined. So we're going to zoom in and look at how the mesh looks like quickly. The mesh looks pretty good here. Done a good job of meshing. And then once we have inspected the mesh, we can go ahead and solve it. And it can solve it. It's quite quick for a for a single point. But when you have multiple points, then you need to do the MATLAB automation to get all the points done quickly. Well, it's still going to take time, but at least you're not sitting in the terminal monitoring the process. So it looks like it has done it. And then let's go and look at the results. So that's your flux lines. You can aid, look at the flux lines from Tesla. That's your density flux. And you can see here, we're going up to 2.1. Okay, not bad for a P2. Color. And then let me show you the MATLAB part of it. So MATLAB part, actually, this is your MATLAB script. And this MATLAB script here, here I just ran a simulation before this workshop. And it took some time. You know, I had to go through all these steps. And then it did this plot, which is a MATLAB, which is your this is a torque calculation. So this is the MATLAB script here. You can see here. I don't know how well you can see it. Are you able to see the script?
Yes, sir.
Okay. So you start with your speed definition, your input current, your phase advance, etc. You can input all of these values, and then you're able to store. You're able to issue commands to FEMM for various, and then you can essentially store the values one by one using these variables. Okay. And I'll put this file in a folder along with all the other files so you guys can study it. And then we'll do the plotting here of the data. And we also store what is called the text files here. So we did the text file, for example, there's a flux text file here. You can see we're storing the various values here. Also, number 4. Let's see here. We have a torque value. So I guess this is at a very high RPM, 500 RPM. That's why we have this. Boxes here for we're able to capture some of the waveforms. You can actually take screenshots of your as you're doing the steps. You can take a screenshot and show them so you can see what is the flux density at various steps. Okay. So I'm going to close this here. So I'll show you what happens when you close this and I run this here. This is my MATLAB script. And so I'm just going to run it. You can see it, how it responds. I move on, and it's going to say what's my max phase current. I say I'm on 5 amps. Actually, I do want to change something. Here's advanced 0 degrees, number of poles accumulate. And here it'll open FEMM automatically, and then it can start running the script automatically and do all the steps. Right? So that's the beauty of having this MATLAB script, which can run on its own and do all the electromagnetic analysis without using it. At least you can see one slide. Take a screenshot, once you complete one cycle. That's the way to automate it. Okay. All right. So that's the end of our workshop, fellas. Thank you for sticking by to the end of this workshop. Any questions I can answer? I think it's a good time, not too bad of a time. Let's see here. So you can still have most of your evenings.
So one question regarding the wire gauges that you were showing in the motor construction in the FEMM software that we were seeing some time ago. So you mentioned that the wire gauges are like 20 or 22, something like that, if I'm not wrong. So is it mandatory that the wire gauges or the wire needs to be insulated or double insulated when it goes on the field, when the motor is going on the field?
No. That is strictly insulated or double insulated wire depends on your application. Okay. So
Okay.
if you have, for example, commercial grade wire, maybe single layer insulation. Okay. Commercial grade motor may be single insulation. Industrial grade may be double insulation. Something which you use in HVAC may have additional reinforced insulation. So, so you have to also look at the insulation rating of your motor, because a lot of manufacturers, when they manufacture the motor, they certify to UL insulation system. So you can have, let's say, class F insulation system or class H insulation system, where you want to make sure your copper wire has that insulation and it has got that temperature rating as well, right? So, but if you're using something for a toy, for example, if you make a motor for a toy, you could probably use a single single layer insulated wire. But if you're using something, let's say for industrial equipment where you're going to have dirt and where you're going to have more of environmental issues, then you want to use something which is heavy duty, let's say class F or class H insulation, and it's double insulated. Does that make sense, Jay?
Okay, yes, yes. And so in case of vehicles, if you were to imagine, so I hope that should also be insulated, right? With a higher
Yes,
degree of insulation
absolutely.
for a
Yeah, you
vehicle
don't.
application.
Right, 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 right. Yeah, it does. It does need to be higher grade of wire. Yeah.
Okay, thank you.
Yep. So, any other questions? So I'll be putting all the videos and the files on a folder so that it is accessible to everybody here. And in the meantime, if you come across any questions, feel free to reach out to me. And I thank you for sticking by, and I give you back at least some of your time. We did not need to take all of the time today to finish the workshop. So hopefully you have enjoyed it. I will be sending out a feedback survey, and I hope that you can fill that feedback survey so that I can use that feedback to improve the workshop. So I thank you for your time. Back into